Hello, students. Anyone else have anything to add about what's happening? What was the discussion that was happening while I was gone? Everybody's quiet now? But what were you guys adding to? Oh, it was just so anyone else have anything to add to nothing? Cool. So quick question. Since you guys are here, you get to decide between days next week for our second exam. Thursday and Friday both work pretty well for me. And they should work well for our schedule as well. So anybody have any thoughts one way or the other with those? Is there something that I need to know about what some other class that a lot of people in this class have scheduled for an exam next week or something? Any major push for one day or the other? Yeah, Hannah, check your schedule for a minute and let me know what you see. My gut is to do it Friday just because it gives everybody one more day to study, which is good. So next Friday would be the 13th. On Friday, Hannah? Do your exams have the all-day window the same way mine do for math? Yeah. So any other conflicts? I mean, I don't have a big problem with that. So I can set it up so that you could take it Thursday if you want to. That would be fine for me. I would rather not set it so that the entire class has a 2-day window to take the exam. There's just too much time there for information transfer, but in a limited sense, that would be fine. Okay, so let's plan on having exam 2 on the 13th, except for you, Hannah, and we can talk about that. Now, the cool thing is that even though all the chapters that we have available for exam 2, we've already covered in recitation time, the great thing is we're still going to be practicing Lewis structures in chapter 7. All right. So chapter 7 has a few different topics. It's kind of a catch-all chapter, but it's all about covalent molecules. So it's sort of like, now that we know how to draw them with Lewis structures, what things can we figure out about them? All right. So the major topics that we have to cover are the shapes of molecules. The fancy term for that is molecular geometry. We have to talk about polarity. Now, we've already talked about bond polarity, but this is molecular polarity, the polarity of a whole molecule. So if a bond can have in our unequal sharing of electrons, then an entire molecule can as well. So we'll talk about how to figure out if a molecule has polarity or if it does not have polarity, if it's nonpolar. And then one of my favorite topics in the Gen Chem curriculum, because the theory can get pretty complex pretty quickly, we have to talk about a few different ways to understand how covalent bonds form, how electrons are shared. All right. So those are the chapter 7 topics that we have to get good at. And the biggest one of them is molecular geometry. So in order to do that, we need a bunch of examples of molecules to talk about different shapes, because there are a number of them. So that gives us a great chance to practice drawing good Lewis structures. All right, so let's draw some Lewis structures, because we're going to use them to illustrate our discussion of shape. So start a brand new page of paper and just start drawing me Lewis structures for all of these. All right, it's going to take us a while, but these are the Lewis structures that we're going to use to inform our discussion of shape. All right, now it seems like a lot of Lewis structures to draw, and it is. So take some time, draw them using our best rules. All right, and I'll sort of enforce a time limit by drawing a line's worth of them at a time every so often. So we need these Lewis structures in order to illustrate our discussion of molecular geometry of shape. And that discussion will take like our whole time today. It's going to be a while, but it's really fun. It's one of the funnest topics in the entire class. right, I'll begin enforcing time. Those are correct Lewis structures for BEH2 and for HCN. And then we go to BF3. Note that boron is an exception to the octet rule here because we're minimizing formal charge. Here's our best Lewis structure for O3, ozone. Note that there is some formal charge in the structure. The central oxygen has a +1 formal charge. The oxygen on the right has a -1 formal charge, but we can't minimize the formal charge any farther because oxygen isn't third row or below on the periodic table, okay? So we can't share one more pair of electrons between these two oxygens to bring the formal charge down to 0 for all 3 atoms. That's our best possible Lewis structure for O3. All right, I'll let you guys work for a few more minutes and then give you another batch. And if one of these structures is not making sense to you, feel free to ask me to explain how I've come up with this as the Lewis structure. All right, there's my third row. And we'll do a couple from the fourth row. Give you another couple minutes to get that last row done. All right. So I'm trying to get some models ready for us to look at here at the same time. So now that we have our list of Lewis structures, why did I organize them this way? All right. The key here is that we use this concept called VESPR, V-S-E-P-R, if I can even write those letters. So VESPR theory is the theory that allows us to predict the shape around a central atom in a small molecule. VESPR, as you might think, is an acronym that stands for valence shell electron pair repulsion. You may not have gotten the acronym all by yourself because that's a big one. All right. Now, that sounds like a very complex theory. Valence shell electron pair repulsion. Wow, that sounds complex. No, it's actually super simple. What it means is that in order to predict the shape around a central atom, all we have to do is understand that electrons repel one another. All right. So how does that work? We have to define something called the number of electron groups around the central atom, the atom that we're trying to decide what shape around the shape around it is. So what is an electron group? An electron group can be a single bond or a double bond or a triple bond or a lone pair, an unshared pair of electrons. Any one of those counts as exactly one electron group. So an electron group is really just a place around a central atom where there are one or more pair of electrons hanging out. Okay? So any of those counts as just one electron group. Now, if we look at our lists of Lewis structures, you'll see that I was very specific in the way I organized the list, because the first two molecules on our list have exactly two electron groups around the central atom. So we're just looking at the atom in the middle right now. How many electron groups are attached to that beryllium? I see one for the single bond there, one for the single bond there, two electron groups. All right. I see one for the HC bond here, one for the carbon-nitrogen triple bond there, two electron groups. So those molecules share a common shape. So not all molecules with three electron groups have exactly the same shape, but they're all very closely related in the way that they look in 3 dimensions. Now, it turns out that the molecules that we've drawn here, BF3 and COH2 and ozone, so I'm grouping those together. In each case, these have 3 electron groups around the central atom. All right. Some books will refer to these electron groups as electron domains, and I use both terms interchangeably. So if you catch me saying electron domain instead, same thing. All right. Both terms mean the same thing. So let's count our electron groups around BF3 or around boron and BF3. I see 1, 2, 3 electron groups, all single bonds in this case. In this case, still 3 electron groups. A single bond counts as 1, single bond counts as 1, double bond counts as 1, 3 electron groups. And then for ozone, also 3 electron groups. 1 for the double bond, 1 for the single bond, 1 for the lone pair. All right. So the fact that all of them have 3 electron groups means that their shapes are going to be very, very similar. All right. We're going to give names to these shapes, but we need to first be able to separate these based on number of electron groups. So you can see that these three structures together each have 4 electron groups. And it turns out that in this case, the electron groups are either single bonds or lone pairs. It doesn't have to be that way. If you think back into your head, for an example like sulfate, SO42-, the best Lewis structure for sulfate had 2 double bonds and 2 single bonds to the central atom, even though we realized because of resonance that all 4 of those bonds are actually 1.5 bonds, all right? But the Lewis structure that we draw has 2 single bonds and 2 double bonds to the sulfur. That's still 4 electron groups. So sulfate would have a very similar shape to methane, for example, CH4. The examples that I've given you here in this row, I've grouped those together because each of those have 5 electron groups around the central atom. And then the last batch, 6 electron groups around the central atom. So the first thing that we have to do to figure out what the shape of the molecule is count the number of electron groups around the central atom, okay? Now, Lewis structures don't directly indicate what the shape of a molecule is, but the number of electron groups around the central atom does indicate the shape of the molecule. So that's the important thing that we're going to want to assess when we're trying to figure out what the shape of a molecule is. So now let's start talking about shape, and to do that, we're going to go each group one at a time, from 2 to 6 electron groups, all right? So let's look at our molecules that had 2 electron groups for a second. And note, there's nothing wrong with me drawing this Lewis structure like this. That's a correct Lewis structure because in that Lewis structure, we have 4 total electrons. That's our skeleton structure. We've used all 4 electrons, so we're finished, all right? We know it's going to be an exception to the octet rule because we don't have enough electrons. There's also nothing wrong with me drawing a Lewis structure like this, where all 3 atoms are in a straight line. The key here is to realize that the Lewis structure itself does not directly indicate shape. What does indicate shape is how many electron groups, all right? So for things with 2 electron groups, if Vesper theory is true, then what we would expect is those 2 electron groups to be as far apart from one another around that central atom as possible. In other words, we would expect that the correct shape for something with 2 electron groups should have an angle between the 2 electron groups of 180 degrees. And because the electron groups in this case are bonds, we call that a bond angle. So what do we call that shape? We named this shape based on the fact that all 3 of these atoms, because of that 180-degree bond angle, are in a straight line. So we call that molecular geometry, that shape, linear. Now, you can memorize these names for the shapes, but to me, it's a lot easier to just know what it looks like in 3 dimensions. And most of the time, the 3-dimensional structure of that molecule is going to indicate what its shape is. The names actually correspond to what they look like in 3 dimensions. Now, the same thing is true with HCN. Even though there's a triple bond and a single bond, those 2 electron groups are still 180 degrees apart from one another. All 3 of those atoms are still in a straight line. The shape of HCN is still linear. So that was easy. When your central atom has 2 electron groups, the shape around that central atom is linear. It's always true. All right. You can't get any different kind of a shape other than having a 180-degree bond angle around that central atom. So that's the only possible shape. So what about things with 3 electron groups? So here are our examples there. BF3, and COH2, and O3. If we had 3 electron groups around a central atom, and Vesper theory says electron groups around a central atom go as far apart from one another as possible. All right, they want to take up as much space around that central atom as they possibly can, get as far away from the other electron groups as possible. What's the farthest that 2 of these 3 electron groups could be apart from one another in terms of angle? "45 degrees? That doesn't look like 45 degrees to me." So if I were to go from this bond all the way around to that bond again, that would be 360 degrees, wouldn't it? So any one bond angle here should be 1/3 of that 360 degrees, or 120 degrees. Now, we're making an underlying assumption in assigning that bond angle of 120 degrees. So be really clear that that assumption's being made, because the assumption isn't going to be true anymore after we get to things with more than 3 electron groups. And the assumption that we're making here is that the farthest apart we can put those electron groups is in the same XY plane, a 2-dimensional plane. Once we get to 4 or more electron groups, we can't rely on just 2 dimensions to describe shape anymore. We have to think 3-dimensionally, an XY and a Z plane as well. But in this case, 120 degrees is the correct answer for the distance between those bonds, the bond angle. Now, how do we name this shape based on the fact that our bond angles are 120 degrees? Remember that right now, all 4 of these atoms are in the same XY plane. All right, the plane of the paper. And those 4 atoms form the rough shape of a triangle, if you look at those fluorines around the outside. So the atoms are in the same plane and they form the rough shape of a triangle. That's how we name this shape. The shape is called trigonal planar. Note that we still have a trigonal planar shape with formaldehyde, COH2. All right, we still have 4 atoms forming the shape of a triangle and all in the same plane. Now, in terms of bond angles, we do have to make some very small adjustments here. Wouldn't you guys anticipate that because oxygen is a much larger atom than hydrogen, and because we've got a double bond instead of a single bond, wouldn't you expect for this electron group to push a little more than those 2 tiny little hydrogens in electron groups? If you expect that, that's actually true. So we have to think about some small adjustments to bond angles here, because bigger electron groups push harder than littler ones do. So we would expect the bond angle here to be a little greater than 120 degrees. We would expect the bond angle here to be a little less than 120 degrees. But still, the basic bond angle is about 120 degrees. So now that we know that things with 3 electron groups tend to have bond angles around 120 degrees, this looks like a pretty dumb way to draw O3. That has 3 electron groups. So if you drew it this way and predicted its shape based on that drawing, you might say that O3 had a linear shape, and you would be wrong, because Lewis structures don't directly indicate shape. This is a correct Lewis structure, but it's a Lewis structure that gives us bad indications of the shape of that molecule. So what would a more correct looking representation of the shape of that molecule look like? Well, we know 3 electron groups tend to be about 120 degrees apart. So that lone pair is pushing those other two electron groups out of being planar, or sorry, out of being linear. So that might be a better representation of our shape. The other thing that we need to realize is that part of VSEPR theory that's been discussed a lot is most of the time, unshared pairs of electrons, lone pairs, actually push a lot harder than shared pairs of electrons do. So because of that, we would expect this bond angle between those two oxygens to be less than 120 degrees, because unshared pairs of electrons tend to push harder than shared pairs do. But still, our basic bond angle that we keep in mind for things with 3 electron groups is about 120 degrees. Now, we cannot call this shape trigonal planar anymore, because this shape is different from this shape, all right? In other words, having a lone pair in place of a bond changes our shape. So how do we name this shape? Well, in this case, we've got 3 atoms, so the shape kind of looks like a linear shape, but the 3 atoms are not in a straight line anymore, all right? When you end up with 3 atoms in a row in your Lewis structure, the shape is either going to be linear if they're all in a straight line, or if they're not all in a straight line, we're going to call that shape bent instead. All right, not a straight line. So those 3 atoms are not in a straight line, so we call that shape bent. And that's it in terms of shapes that we can get for molecules that have 3 electron groups around the central atom. Now we get to the place where the crap hits the fan a little bit. All right. So molecules with 4 electron groups around the central atom. CH4 was the first one of those that we drew. And this is a perfectly fine Lewis structure representing methane, CH4. Lewis structures do not directly indicate shape. And it's a lot harder for us once we get to 4 or more electron groups to actually think through what the shapes of the molecules are, because they're 3-dimensional. All of the bonds are not in the same XY plane. So this is a model that sort of represents a way that we could get those electron groups as far apart from one another as possible. The center of the model is our carbon, and each of the legs goes out to a hydrogen. If this were an accurate portrayal of the shape of methane, then we would expect the bond angles to be 90 degrees. They are not 90 degrees. As a matter of fact, it's a very intriguing geometric problem to start with a center mass and then try and get 4 individual things as far apart from one another as possible around that central mass. Using just geometry, we could derive that bond angle. I'll just give you the answer because it's a long derivation. It's not very pleasing anyway. It turns out that when we have 4 electron groups around a central atom, our bond angles end up being something close to 109.5 degrees. if those 4 electron groups are all exactly the same as one another, like in this case, the bond angle is 109.5 degrees. Note that I've had to draw this in a 3-dimensional representation. So these 3 atoms are all in the plane of my paper. This atom that I've represented with a bond that is wedged is sort of coming out at us. So I'm using the model now to represent this. So imagine these 3 are all in the plane of the paper. This one is coming out at you, and that one is going away from you. So we represent things that are going away from us with dashes. You have to use your imagination a little bit to rationalize what we've named this shape. So if you think about these 3 hydrogens forming one face of a geometric figure, and then these 3 hydrogens forming another face of a geometric figure, and the back 3 hydrogens forming another face of a geometric figure, and then the bottom 3 hydrogens forming a 4th face. I've not done a great job of drawing this, but each of those 4 faces would be exactly the same size. So we have a 3-dimensional figure where all 4 faces of the figure are exactly the same size. The name that we give to those kinds of geometric 3-dimensional figures is a tetrahedron, all right, a 4-sided figure. So because of that, the shape that we name here, we call it tetrahedral. This model kit's terrible. So I'm going to give you guys a tool to help you visualize these in 3 dimensions. All right. And I think it's a tool that is present in our lab sequence as well. So in the upcoming lab that talks about molecular geometry, you will go to this website, and from there you can load in a Lewis structure or a chemical formula, and they'll give you the 3-dimensional shape of that Lewis structure. All right. So this is what CH4 looks like in 3 dimensions. You can see that all of the bond angles between the hydrogens are exactly the same as one another, even though it may not look like it in any one representation. If we rotate that model, we can see that all those bond angles are identical. As a matter of fact, we can even calculate the bond angle using this tool. So if I go to angle over here and click on it, I can click any 3 atoms that form a bond angle, and it'll measure the angle for me. So I'm going to click 1, then 2, then 3. Maybe I didn't click hard enough. There we go. And it's measuring my bond angle as 109.5 degrees. So why don't we load in our next model? And our next model is was it NCl3? Did I do NCl3? I don't know anymore. I think it is. So if I go to load models by name, I can put in a common name or a systematic name. So let's try nitrogen trichloride. Am I going to post a link to Canvas for this, Hannah? Is that what you're talking about? The link is already in Canvas. If you look at your next lab, then the link is in that lab. So here is NCl3. Notice that it looks a lot like CH4, except one of our 4 electron groups is sort of just erased. It's not actually erased. That lone pair up there doesn't show up in the model. All that shows up in the model is atoms. So that's important because when we name shapes, the shapes are named based on the position of atoms, not on lone pairs. So lone pairs affect the shape because that lone pair there pushed these other 3 atoms out of the same plane. So if we were drawing a 3-dimensional representation of this instead of using the model to do that, what would it look like? Imagine this being our 3-dimensional representation of CH4. We can do a similar thing with NCl3, except we're just going to replace one of those bonds with a lone pair. So we're still going to have a chlorine coming out at us and another going back into the paper. So that is a rough representation of the shape of NCl3. And I'm going to try and make my model look as much like that as possible. There we go. All right, there's the top of our model with the lone pair. There's our chlorine coming out at us, going back into the paper, and that chlorine and nitrogen are in the same plane as the paper or the computer screen, whatever. So we can't name this shape tetrahedral anymore because even though we could rationalize that there's a 4-sided figure sitting in here someplace, the 4 sides aren't the same size anymore. Instead, the way we name this shape is if you imagine those 3 chlorines forming the bottom of the 3-dimensional structure, it looks like a 3-sided pyramid, all right, where nitrogen is the cap of the pyramid. So a 3-sided pyramid is what this thing looks like. So chemists gave this the name trigonal pyramid. That's the name of this shape. Note that our bond angles here should still be pretty close to 109.5. Remember that lone pairs tend to push harder than unshared pairs of electrons. So if we had to guess what that bond angle is, we would guess that it was probably a little less than 109.5. But chlorines are pretty big, so they might even push a little harder than a lone pair, all right? Just remember that lone pairs tend to push harder, which means that they tend to compress the bond angles near them to make them a little smaller than 109.5. The cool thing is we can actually check our bond angle here. So let's check. So it looks like the bond angle is actually a little greater than 109.5. What does that mean? That means that a bonding group with chlorine is big enough to push a little harder than a lone pair is. That doesn't mean that we would have to predict that. As a matter of fact, I'm telling you that most of the time, lone pairs, unshared pairs of electrons, actually push harder than shared pairs do. This is a case where that isn't necessarily true. We'll look at another case where it's certainly true in just a minute here. All right. So, do I want you to remember specific bond angles for specific models? No. I do want you to remember that for things with 4 electron groups, the basic bond angle you want to keep in mind is 109.5. You should remember that. Also, you should remember that generally speaking, lone pairs push the bond angles around them to be smaller than they normally would. Lone pairs push harder than unshared pairs do. All right. In this case, because those chlorines are so big, that doesn't turn out to be the case. But generally speaking, it's a good prediction to make. Now we still have one more model to look at for something with 4 electron groups, and that's water. So I drew water in the most stupid possible way that I could draw it, but still, well, I suppose I could come up with even stupider ones. Still, that's a correct Lewis structure, because water and Lewis structures in general do not indicate shape. So if we want to draw this thing based on the fact that we know it has 4 electron groups around the central atom, the easiest way to do that would be to put the 2 groups that are bonds in the same plane as the oxygen, and then pretend that one of those lone pairs is going out away from us and another is coming out toward us. That should be the shape of water based on the fact that it has 4 electron groups. Now, what about bond angle? 4 electron groups means we're talking about something close to 109.5. The fact that lone pairs push harder than unshared pairs in a general sense means we're expecting this bond angle to be something less than 109.5 for water. So let's load water into our model and check it out. Note that in this case, I could just put water in here and it would load that like the name water. I can also use chemical formulas. I'm going to put in H2O, and that loads just fine as well. So indeed, it looks like water is definitely not linear, all right, if we calculate a bond angle. Quite a bit less than 109.5. So how do we name this shape? Remember that whenever we have 3 atoms in a row in our Lewis structure, we have to name the shape based on whether those atoms are in a straight line or whether they're not in a straight line. These atoms are not in a straight line, so the shape name here is bent. We can have a bent shape with bond angles of 120 degrees or 109.5. They're both bent. It's just water is more bent than ozone is. We are at about an hour. Let's take a quick break and then we'll come back and talk about the rest of our shapes, things with 5 and 6 electron groups. All right. So let's do like 6 minutes. Come back in 6 minutes. It'll put us at 10:12. All right, we're back. So I have dropped a link into the chat that should help you guys out a lot. Hannah, I think I may even replace the link that is in our lab for next week with this link instead, because it does the same thing, but it's actually a much better tool. So I'm going to use that tool now to start talking about the Lewis structures that have more than 4 electron groups around the central atom. Yeah, save this link. All right, just bookmark it. It's awesome. It's amazing. So let's check it out. I gotta share my screen. And I think we did PCl5. I gotta look back. And SF4 and XEF2. Okay. Your brain was not ready for this. Hannah, this is a really hard concept. All right. When I tell you that in high school, especially in AP Chem, I really struggled with chemistry. This is one of the things that I really struggled with a lot, among like a number of other things. It started to click more for me at the very end of the year, but in all honesty, like chemistry in high school was really hard for me, and this is one of the things that I really struggled with and continued to struggle with even when I studied chemistry in college. And like I never had majors level first year chemistry in college because I did well enough on the AP exam that I moved past it. But even like when I studied organic chemistry, which is a sophomore level majors organic course, thinking about shapes, three-dimensional shapes of molecules is a really important part of that course too. And I continued to struggle with it. So it turns out that people that are good at math and calculation often are not good at this kind of thing, which is like spatial reasoning. All right. And it's because a lot of times people don't practice this. People that are artists tend to already be good at this kind of reasoning. So my wife, who is an artist, when I started showing her these three-dimensional shapes of molecules when I was in grad school and thinking about them a lot, it made like instant sense to her. It was not even a struggle for her at all. And that made me sick because I had to spend so much time getting decent at being able to wrap my head around what these things look like in 3 dimensions. All right. That was my reminder to myself to unpause the recording so that I didn't cut off the last half of our lesson. I've done that twice, so I'm going to write to myself every time I pause the recording so that when I come back, that doesn't happen again, because it's a disaster when it does. All right, so let's look at PCl5 in terms of its three-dimensional shape. When things have 5 electron groups, this is by far the hardest one of them to visualize, even harder than things with 6 electron groups, because the bond angles are kind of weird. It turns out that the first 2 bonds end up being 180 degrees apart from one another. So in the three-dimensional shape, you can see that the top and bottom chlorine right now are 180 degrees apart from one another. All right. Whoa. How do I zoom out? How do I zoom out? What did I just do? I have a trackpad. Scroller in the middle. Oh, yeah, I don't have a mouse. I wish I had a mouse. So I probably used my scroller someplace on this trackpad, which is a little fumbly. And that's probably why I zoomed in. So those 2 electron groups are 180 degrees apart from one another. What I'm going to try and do now is I'm going to try and flip the molecule 90 degrees. So this atom and this atom and this atom are all in a straight line so that we're looking right down those 3. And we'll look at what the bond angle looks like between these 2 instead. You bastard. All right, there we go. So it looks like our bond angle here is 120 degrees, a third of a way around the circle. And that's true. All right, so the bond angles for the, we'll put a dash, wedge. Here is how I would represent this with a drawing. Now, still, we have to keep in mind that our bond angles aren't going to look perfectly the way they are in real life, because we're representing a 3-dimensional figure with a 2-dimensional drawing. So the bond angle from here to here is 180 degrees. The bond angle from here to here, 120 degrees. What about the bond angle from here to here? From any one of these three chlorines to one of the chlorines on the top and bottom. What's the bond angle between those two? What does our bond angle look like from one of those chlorines on the top and bottom to one of the ones around the middle? Yeah, it is 90 degrees. Very good. So 180 and 90 and 120 are all bond angles that can show up in things with 5 electron groups. And the reason why is because having those things as far apart as possible, because 5 is a weird number, gives us this weird thing where some of the electron groups are arranged a little differently than the other ones. All right. As a matter of fact, we organize those different types of electron groups by naming them differently from one another. All right. So the 3 that are around the outside, sort of like the waistband. Oh, you guys can't see that because I have the wrong screen up. The 3 that are starred here and here and here, the ones that are sort of the waistband around the middle, we call those equatorial positions. And the ones at the top and bottom, we refer to those as axial positions. Hannah, I'm sorry, those are big words, and you've already said your brain wasn't ready for this, so that's like even more brain busting than before. But those are just big terms that talk about what those shapes are, what those places look like. So equatorial, what does that mean? Like the equator? So we're talking about the 3 positions that are around the middle, all right? And axial at the 2 axes, the top and bottom. Now, it's really important for us to be able to distinguish the equatorial from the axial positions, because right now we have a molecule where all 5 of the positions are filled with atoms. But next, we're going to be talking about where 1 or 2 of those positions are filled with unshared pairs, with lone pairs, instead of with atoms. Okay? So what do we call this shape? You have to use your imagination a little bit. All right, let's use our imagination and imagine that we basically have a 3-sided pyramid on the top. So those 3 chlorines, for example, forming this face of the pyramid, and another 3-sided pyramid on the bottom. Like, for example, those 3 chlorines forming this face of that pyramid on the bottom. So because we have a 3-sided pyramid on the top and another on the bottom, the name that we give to this shape is trigonal bipyramid. Now, some books will even turn this into an adjective instead of a noun and call it trigonal bipyramidal, but that just sounds funky to me, so I don't conjugate that bipyramid. So trigonal bipyramid. Now, what if we turn one of those 5 electron groups into a lone pair? So that's the example that when we get to SF4. Now, the important thing to realize is that we could put the lone pair in one of the axial positions, or we could put it in one of the equatorial positions, and that would give us a very different shape depending on where we put the lone pair. So it turns out that whenever we put lone pairs into a model that has 5 electron groups, they always go equatorial. And the reason why is because, remember, lone pairs push harder than bonded pairs. So we want to give the lone pairs particularly as much space as possible. Now, imagine if we had a lone pair in one of the axial positions. If we had a lone pair in one of the axial positions, it would be only 90 degrees away from 3 other electron groups. That's pretty bad, all right? That lone pair is very close to 3 other electron groups. Whereas if we had a lone pair in an equatorial position, it would be 90 degrees away from only 2 other groups. So having the lone pair in an equatorial position gives it a little bit more space, which is why whenever we put lone pairs into a model with 5 electron groups, they always end up in equatorial positions. So here is our Lewis structure for SF4. The bond angles are not 90 degrees, at least not all of them. So imagine whatever we did with PCl5, we're going to have a similar thing with SF4, but we're going to replace one of those equatorial positions with the lone pair. Now, I'm not even going to draw in all the unshared pairs of electrons on the fluorines because you know they're there, and it's not really important to our discussion of shape anyway. That is a basic 3-dimensional representation of the shape of SF4. Now, this is one of the ones where your spatial brain may need a little practice to get the right name for the shape here. So let's load SF4 into our 3D model. First, I'm going to try and rotate this thing so it looks a lot like our drawing. Note that the bond angle between those 2 axial positions, not perfectly 180 degrees anymore. So why would that bond angle be slightly greater than 180 degrees now? It's not tetrahedral. So Ezra, the one lone pair over here is pushing harder than any of the bonded pairs, which is why it pushes this angle to be just slightly greater than 180. Or if you measure it in this direction, slightly less than 180, all right? So slight deviation from 180 degree bond angle here. Now, how do we name this shape? I'm trying to move it into a different context so that we can, come on, why are you actively fighting against me? All right, we're getting better now. So this is about the best way that I could situate this thing to make it look like what we named this shape. So imagine the 2 axial fluorines here, almost in a straight line, and then the 2 equatorial fluorines forming a little base here. If you use your imagination, and I don't know if kids play on these anymore because they're dangerous and we sort of like sanitized the recess area, but we used to do things where, like, I was always big for my age, so somebody that was really little would sit on the other side here, and then I would jump and launch them into the air really high. What do we call that piece of playground equipment? A seesaw. And as a matter of fact, that is one of the correct names for this shape, is the seesaw shape. All right. The other correct name for this shape is another name for this piece of playground equipment. So the older name that we used even before seesaw was, anybody know the other name? Teeter-totter, that's right. So teeter-totter is also a correct name for this shape. Either one of those names is correct, and it's basically because that's what it looks like in 3 dimensions. All right, so this one's really hard to see based on the drawing that I gave you guys. You got to sort of tilt it 90 degrees to the right in order to make that happen. So those two fluorines form the planks of the seesaw, and these two, the axial ones, form the base of the seesaw. Now, Hannah, if this spatial reasoning just doesn't work for you, there's another way for you to get when something is seesaw shaped. Because if these things are both true, if your central atom has 5 electron groups on it, and if one of those 5 electron groups is a lone pair, the shape around that central atom is always seesaw. Easy enough, right? As a matter of fact, we can redo this entire list where just based on how many electron groups there are and how many out of those are lone pairs, that always tells us the shape. So if you want to memorize that instead, it gets you to the same place, but you got to memorize it instead of just being able to look at this shape after you draw it and say, that looks like a teeter-totter. I prefer that looks like a teeter-totter because that sort of spatial awareness has come to me after working on it for years. All right. So for somebody that doesn't look like a teeter-totter to right away, you might want to remember it the other way. Okay, so now how do we look at something like XEF2? XEF2 has 3 lone pairs on the central atom. Oh, crap. I may have left one out. I may have left an important one out of our discussion. I did. All right. So let's do one more together on the fly, straight from the Lewis structure. So I should have given you guys BRF3. That's an important one. Draw me the best Lewis structure for it. Guess what? It's going to have 5 electron groups on the central atom, and 2 of them are going to be lone pairs. So if that's our best Lewis structure for BRF3, what is that going to look like, something with 5 electron groups, when we put it into a 3-dimensional rendering? Remember that those lone pairs are going to end up in equatorial positions. All right? So two of those 3 equatorial positions are lone pairs, and the third one is another fluorine. So that is a decent 3-dimensional rendering of BRF3. Let's load it, and then you can realize that it is actually pretty good. Apparently those are not in the list. I'm trying to find something with 5 electron groups that fits, that is in the list. So it looks like we don't have a complete list either place. What a bummer. I'm trying to find something that has the correct number of electron groups and lone pairs here. What else might we try for something with 5? The book has CLF3. Well, let's try that. Hey, all right. I don't know why BRF3 is not listed anyplace. That molecule exists. So does IF3. Weird. Whatever. But at least we have something from the list, okay? So BRF3 would look exactly like this, except it would have bromine in the center instead of chlorine, but whatevs. So you can see that our bond angle here is pretty close to what? Pretty close to 180, all right? Those two axial positions are staffed with chlorines, or sorry, are staffed with fluorines. And then our two lone pairs are in equatorial positions, and that's our third equatorial position there. I'm trying to make this look as much like my picture as possible. So there we go. Now the name for this shape actually comes down to the fact that it looks a lot like a letter from the alphabet. I'm trying to rotate it. The rotation for this tool is not the best. Now we're getting close. So in 3 dimensions, this shape looks a lot like the letter T. And that's how we name this shape. So BRF3 is T-shaped. Now, here's the crazy one, all right? And this is insane. XEF2 has 5 electron groups around the central atom. 3 of those groups are lone pairs. Remember that no matter how many lone pairs we have on the central atom, and there can never be more than 3 out of the 5, the lone pairs are always going to go into equatorial positions. So if we draw this shape based on the fact that the lone pairs will end up in equatorial positions, we end up with 3 equatorial lone pairs, and then we end up with 3 atoms where the bond angle between these 2 electron groups should be exactly 180 degrees. How can you have a bond angle of 180 degrees with 5 electron groups? It turns out that you can. All right, so let's load our model and see if it's not going to give us XEF2. Try I3 minus. So I3 minus ends up with the exact same geometry. All right. Our 3 equatorial lone pairs are around that central iodine. And then we have a bond angle of 180 degrees between those 2 bonds. So what do we call this shape? Remember, anytime we have 3 atoms in a row, they're either going to be in a straight line or they're not. So this shape, XEF2 or I3 minus, it's linear. Just making sure that I write down the names of each one of these. All right, so that's why things with 5 electron groups are, frankly, a pain in the butt. Because with 5 electron groups, we can have any one of 4 different shapes. All right, so 5 electron groups, if all 5 of them are bonds, then we're talking about trigonal bipyramid. If one of those 5 is a lone pair, we're talking about seesaw. If 2 of the 5 are lone pairs, we're talking about T-shaped. If 3 of the 5 are lone pairs, we're talking about linear. 4 different shapes that are possible for things with 5 electron groups. All right. The others aren't nearly as bad. So now we'll talk about things with 6 electron groups, and we only have 11 minutes, so let's make sure that we get that done. All right, so SF6, if we have 6 electron groups, it turns out that we don't have axial and equatorial positions anymore. The only bond angles that we can end up with are bond angles of 180 degrees or bond angles of 90 degrees. So the bond angle between these two, 90 degrees. The bond angle between these two, 180 degrees. The bond angle between these two, 180. The bond angle between these two, 90. So for things with 6 electron groups, your bond angles are 180 degree bond angles or 90 degree bond angles. So if this is a basic 3-dimensional representation of SF6, note that I'm not drawing in all the lone pairs for all those fluorines because they don't matter with respect to the shape of the molecule. All right, we're just talking about shape now. This looks like a geometric figure that has 8 identical sides to it. All right, it's going to be hard for me to draw this well. Because I'm bad at the arts. Oh wait, those all have to go down to the same place. Oh God. So an 8-sided figure where all the sides are the same size. That's my feeble, horrible attempt to draw that. All right, I'm not very good at it, but we can load the model instead, and that might be better. There we go. So it turns out that because this thing looks like an 8-sided figure, if you think about it 3-dimensionally, and the atoms are actually taking up the amount of space that they should, 8-sided figures where all the sides are the same size are called octahedrons. So we call this shape octahedral. Now the cool thing is here that if we were to replace one of these 6 electron groups with a lone pair, like for example, if we had BrF5, it wouldn't really matter which of the 6 electron groups we replaced, which of the domains we replaced, because all of them are going to give the exact same shape anyway. So BrF5, one of our 6 electron groups is now a lone pair, and the remaining ones look the same way that they did in SF6. So that lone pair is still pushing those other electron groups up and out of the way. And the resulting shape of that now looks like a pyramid with a square base. So these 4 fluorines now form the base of a 4-sided pyramid. So because it's a square-based pyramid, we call this shape square pyramid. Let's try and load a model that will make sense of that for us. All right. Hey, there we go. Sweet. So there's BrF5. You can see these 4 fluorines form the base of our pyramid, and that fluorine forms the apex. Our lone pair is sitting down here. It just doesn't show up in the model, but it's still pushing those other groups out of the way. And then finally, XEF4, which is in the list because I saw it a minute ago. So xenon tetrafluoride, let's load it. There's what xenon tetrafluoride looks like. Remember that lone pairs want to be as far apart from everything else as possible. That is doubly true about lone pairs being as far apart from other lone pairs as possible. So if we have to replace 2 of our 6 electron groups in this kind of shape with lone pairs, we're going to want to put the lone pairs 180 degrees apart from one another on opposite sides of the molecule or of the central atom. So for XEF4, we're going to represent a lone pair on the top and on the bottom, and then the 4 remaining electron groups. Form a plane around the center of the molecule. So note that this is approximately what I have drawn in my drawing. I can't get it perfectly up and down. But there's one of the lone pairs, there's the other lone pair. Now, how do we name this shape? In this case, our bond angles are 90 and 180 degrees, and all 5 of our atoms here are in the same plane. All right, they're all in the same XY plane. So because all of these atoms are in the same plane, and the plane forms the shape of a square, that's how we name this last shape. All the atoms are in the same plane. The plane forms the shape of a square. So this shape is called square planar. Any questions about any one of these shapes? So Hannah, this is just for you, okay? Quick recap in our last 4 minutes. If we have 2 electron groups, you're never going to have any lone pairs around the central atom. Your shape for things with 2 electron groups around the central atom is always going to be linear. If we have 3 electron groups around the central atom and none of those 3 are lone pairs, our shape is always going to be trigonal planar. If 3 electron groups are present around the central atom and one of those 3 is a lone pair, our shape is going to be bent. If we have 4 electron groups around the central atom, none of them are lone pairs, our shape is tetrahedral. If we have 4 electron groups around the central atom and one of those 4 electron groups is a lone pair, then our shape is trigonal pyramid. If there are 4 electron groups and 2 of those electron groups are lone pairs, our shape is bent, like water. Holy crap, I did the exact right number of lines. That was very fortunate. If I have 5 electron groups and none of them are lone pairs, then my shape is trigonal bipyramid. If I have 5 electron groups and one of those 5 electron groups are lone pairs, then my shape is seesaw. If I have 5 electron groups and 2 out of the 5 are lone pairs, my molecule ends up being T-shaped. If I have 5 electron groups and 3 of them are lone pairs, the shape around that central atom is linear. If I have 6 electron groups and none of them are lone pairs around that central atom, then my shape is octahedral. There are some very old references that refer to octahedral as square bipyramid. That's acceptable too. I don't like it because it's not as common to refer to it that way, but it's something that most chemists would understand. So I'm fine with it if you forget and name it the other thing. If we have 6 electron groups and 1 of the 6 is a lone pair, my shape becomes square pyramid. If I have 6 electron groups and 2 out of those 6 are lone pairs, then my shape is square planar. Now, this seems like a lot of information to memorize, which is why I prefer you not memorize it and instead just get good at thinking about what molecules specifically with 4 and 5 and 6 electron groups look like in 3 dimensions, because those are the ones that we have to visualize in 3 dimensions. So once you can visualize what each of these shapes looks like in 3 dimensions, when you draw a Lewis structure with that number of bonds and lone pairs, the shape will just stick out in your head because most of them look like what their name is. Any more questions? That was a jam-packed time together. All right. Yeah, lots of shapes out there, especially since we get to go all the way to 6 electron groups around a central atom. It's kind of complex sometimes. So when you're studying, think about number of electron groups and number of lone pairs. And also remember to think about the bond angles for each one of these numbers of electron groups. All right. The one with 5 electron groups is the hardest because there are 3 different kinds of bond angles we can have there. With 6 electron groups, it's easy. Your bond angle's either going to be about 90 or about 180. All right, if you guys don't have any more questions, then next time that we're together, I will give you guys a few practice problems and ask you to tell me about the shapes of them. And then we're also going to talk about the polarity of molecules next time. All right. So that's coming up next time. Any more questions before we're done? Remember also that our exam is, I think, going to be on the 13th, if I remember right. Next Friday is the plan. Yeah. Okay. If you guys don't have any more questions, then, oh, something just came into the chat. Yeah, Hannah, I got you. I was talking about the class. You're an exception because we've already talked about it. All right. Okay. Thank you guys very much. And I will see you next time we're together, which will be Friday. All right. Have a wonderful day, everybody.